Have you heard this?
Yes. Mm-hmm.
Very much.
Please let in, yeah. Mm-hmm.
You give me the permission, Barbara?
Anna.
Ah. Okay, so I think that it's time to start our colloquium of Jerzy Pniewski and Leopold Infeld colloquium. It's my great pleasure to introduce today's speaker, Dr. Quigg from Fermi National Accelerator Laboratory. He's an American theoretical physicist, very well known, and he is now a distinguished scientist at Fermilab in Batavia near Chicago. He worked on many different topics in particle physics, starting from electroweak symmetry breaking, and then he devoted a lot of time to super collider physics. And there is a paper that he wrote many years ago. This is what is called ELK paper on super collider physics, which now has more than 2,500 citations. So it is a very famous paper. And then worked also on ultra high energy neutrino interactions, heavy quarks, strong interactions. And his essential theme is the interaction between theory and experiment. And he devoted much of his energy to define the future of particle physics, working on new accelerators. And now he works on a physics program, experimental physics program at Large Hadron Collider, with special attention to electroweak symmetry breaking, quarkonium spectroscopy, and new mesons found there. And today he will talk about Noether's theorem on the occasion of 100th anniversary of publishing a paper in which this theorem was formulated. So Chris, welcome very much. And now the screen is yours. Thank you.
Thank you very much. I'm very happy to be with you in this technologically assisted way. I wish we could be present together, but we're lucky to have this means of doing it. So I wanted to start by paying tribute to my Polish grandparents, with whom you see me here. There's a young scientist surrounded by his grandmother and grandfather. Unfortunately, it was the tradition in immigrant families at the time that I knew my grandparents that the original language, so in our case, Polish, was the language in which the grown-ups had secrets. And so my knowledge of the language was kept to a minimum. I learned only a few very important words. So from my grandmother, things like Kolumki and so on, and from my grandfather, Nostrovia. So that is basically the extent of my knowledge of the Polish language. They could have given me a bigger gift, but they had their reasons. So on the 26th of July in 1918, Felix Klein gave a paper presentation to the Royal Academy of Sciences in Göttingen. Klein is a highly distinguished mathematician with a long career in Göttingen. He's known in popular culture as the person who conceived the Klein surface or Klein bottle, sort of the generalization into, depending on how you count, 2 or 3 dimensions of the Möbius strip. The paper that he presented was not his own work. It was work done by a young colleague, Emmy Noether, and presented to him on the occasion of the 50th anniversary of his doctoral degree. So he was reading this paper on her behalf because she was too young and she was also a woman and therefore didn't have the standing at the time to make a presentation to this august body. It was a very busy time in Göttingen. Not only was Felix Klein celebrating the 50th anniversary of his doctorate, but he had himself, the week before, presented a paper on joint work with his colleague David Hilbert, they had been puzzling over an aspect of the general theory of relativity in which energy conservation didn't seem to arise in the usual way. It was expressed in terms of an identity rather than a constraint. And so to them, it puzzled them that it didn't seem to make a constraint of the kind that we normally experience in other theories. And it was actually for this reason, because of their work, that they had sought the assistance of Noether, knowing that she had experience that would help them come to terms with this question. The photograph of Hilbert that you see is actually from a postcard, a series of postcards produced by one of the bookstores in Göttingen, in which famous professors were depicted, so students could buy these and send them to their parents to prove that they were studying and not drinking beer because they had come into contact with the great men of the time. So there is Mr. Hilbert looking quite splendid, I must say. Noether herself had, on the 23rd of July, presented to the Mathematics Club the statement of her theorems. I should say that throughout the PDF that you can get of these slides, there are lots of links, lots of hidden links, which will take you to the original copies of the paper and to other resources in case you want to pursue them. So here is the title page again of her paper, the one read by Felix Klein. And on the right-hand side is what I consider to be the best English translation of the paper. It's in a book by Yvette Kosman-Schwarzbach called The Noether Theorems, in English, which is itself the translation of a French version. Yvette is a French mathematician who's taken an interest in both the substance of Noether's theorems and of Noether's life. So it's a really excellent representation of the book. What I've highlighted here is the essential feature of Noether's work on this subject, which was to combine the methods of the calculus of variations, so the Euler-Lagrange equations, we might say, in terms of our courses in mechanics, and Lee's theory of groups. He was particularly motivated by the little booklet by Maurice Galois on the beginnings of Lie theory. And her genius, or her insight, was to combine the analytic calculations that we make using the Euler-Lagrange equations with the symmetry principles that are incorporated in group theory, and in particular in the theory of continuous groups. So here, in her own words, rendered in English, are the substances of the two theorems that are contained in this paper on invariant variational problems. Number one is if the integral is invariant under a finite continuous group, G rho, with rho parameters, then there are rho linearly independent combinations among the Lagrangian expressions that become divergences, therefore conserved quantities. And conversely, that implies the invariance of the integral under the group G rho. So this makes a connection between symmetry principles, conservation laws. It works in both directions, going from a symmetry principle to a conservation law and backwards, linking a conservation law with a symmetry principle. Then there's a more general form, which constitutes theorem 2. And again, in the language that she used, if the integral is invariant under an infinite continuous group, depending on rho arbitrary functions, so not just shifts, but arbitrary functions, which means in our language, local variations, so changes in conventions, not just once overall, but independently at every point in space and time. And their derivatives up to order sigma, so no restriction to first derivatives. Then there are rho identities among the Lagrangian expressions and their derivatives up to order sigma. And here as well, the converse of Valen. The paper that involves the proofs, not just the statements, but the proofs of these theorems, is appropriately involved and intricate, and it takes a good deal of effort to follow and reproduce the arguments. But there they are, there are the statements. The first of these includes all the known theorems in mechanics concerning first integrals or conservation laws, and we'll see what those are in just a moment. And the second is the basis that we use for developing gauge theories of interactions. And it was described at the time as the maximum generalization in group theory of general relativity. So 1918 becomes at a time when general relativity was new and sensational, but quantum mechanics had not yet been invented. And this, in fact, inhibited some of the adoption of Noether's theorems to make theories of the fundamental interactions. Indeed, it was also true at the time that only a couple of fundamental interactions, electromagnetism and gravitation, were known. So here are the elementary consequences of the first theorem, which is usually what the form in which we learn Noether's theorem in elementary courses. That translation in space, the notion that there's no preferred location for the laws of nature, leads to momentum conservation. And we would now say, having seen the statement of the theorem, that momentum conservation implies translation in space for the laws of nature. Similarly, the idea that there's no preferred time, that the laws of nature are the same at all times, is linked with energy conservation. The third useful conservation law, angular momentum conservation, is linked to rotational invariance, the absence of a preferred direction for the laws of nature. And then there's sort of a technical statement that if you make boosts, Lorentz transformations, reflecting the idea that there's no preferred frame, all the elements in a classical mechanical system, say of point particles, move along in the same way and have the same configuration. This is not really a conservation law in the usual sense that we use it, but is what is sometimes called the center momentum theorem, a more formal statement. Now, all of these were known at some level before Theorem 1, of which they are special cases. And so I think at the time, part of the reason that physicists in particular didn't pay enormous attention to Theorem 1 is that they saw these consequences and said, well, we've already known that, or we do it in a case that may be a special case, but is general enough for our uses. So it took a while for the recognition of Noether's theorem to become widespread. In fact, you can say that in the world of physicists, it took nearly 50 years for its implications to be really understood. And nevertheless, it is really a dramatic development. These quantities that we know to be the subjects of conservation laws in classical mechanics developed, after all, over time by trial and error, going back hundreds of years, even in the time of Newton and Leibniz and Voltaire and others. There was debate over what the conserved quantities were. Eventually, they were the things that we now call kinetic energy and momentum and so on. And Professor Jerzy, who some of you may know as a very famous group theorist, theoretical physicist of a slightly earlier generation, wrote in the introduction to Noether's collected works, before Noether's theorem, the principle of conservation of energy was shrouded in mystery, leading to the obscure physical systems of Mach and Ostwald. Noether's simple and profound mathematical formulation did much to demystify physics, transforming these mechanical constructions into statements about symmetries. Theorem 2 contains the seed of gauge theories, the idea that symmetries dictate interactions in the language popularized by C and Yang, and shows us just how there is a kinship between general relativity, derived from general coordinate invariance, and the gauge theories derived from symmetries under internal symmetries, internal quantum numbers. And on the way, it clarified Klein and Hilbert's thinking about the energy conservation and general relativity, although one can argue that that really wasn't settled until the early 1960s. It's interesting that the generalized symmetries of Theorem 1, the ones that go far beyond the conservation laws that we learn in classical mechanics, also anticipate the conservation laws of things like solitary waves. So here I show you some colliding solitary waves. These are the Quigg equations, nonlinear solitons that represent the lumps of water that travel for large distances without losing their shape. What I show here is the collision of two solitons, 3, 4, and 5. Look first at two solitons colliding together. What you see is that as they come together, this in reality in a physical system would be the higher amplitude soliton, which moves at a larger velocity, overtaking the slower soliton. They distort each other in a nonlinear way. And then with a phase shift, they go off, recovering their initial shapes. And brilliant work done in the 1960s by applied mathematicians. This characteristic was traced to an infinite number of conservation laws, a whole hierarchy of conservation laws that apply to the Quigg equations and other equations. And so there's a link back to symmetries, rather obscure symmetries in this case, that underlie the conservation laws. So who was the person who did this? Noether was born in 1882 in Erlangen, a university town just north of Nuremberg and a bit north of an hour by train from Munich. He was born into a family of university people. It's a university town. Here is a photo of the university at around that time, the main university street at around that time. The famous son of Erlangen was Ohm, the giver of laws about current and voltage and resistance. He was born in Erlangen, took his PhD at the university there, although this very imposing statue of him is from the Technical University in Munich, downtown in Munich. Noether's father was a mathematics professor himself, a man of some distinction. He worked in algebraic geometry, study of curves on surfaces, their analytic properties, and he was elected to many scholarly academies at the time: Berlin, Göttingen, Munich, Budapest, Copenhagen, Turin, and so on. So a well-known person in his own right. Felix Klein had spent a few years in Erlangen before Emmy's birth. And in his inaugural address at that time, there was a tradition that new professors appointed to high ranks would not only give seminars to introduce their work to their colleagues, but also would give more general seminars to be open to the university community as a whole. And in these lectures, Klein set out a plan for the research he intended to carry out in Erlangen. It became known as his Erlangen program. And the plan was to study geometry from the perspective of group theory. So to characterize it in a very simple-minded way, to move from dealing with, say, Euclidean coordinates to describe geometrical shapes and occurrences to the study of their symmetries and how that impacted them. This became a very well-known program in mathematics, and mathematics related to physics, and the basis for the work of many other people, carried out by Klein, mainly outside Erlangen. He was there only for about 3 years, but it was there that he enunciated this program. Some of the other important figures were people known to physicists. So Alfred Clebsch was a elder collaborator and mentor of Max Noether. And his collaborator, Paul Gordon, was a longtime professor at the University of Erlangen. Physicists, at least those over the age of 50, will know what these mysterious tables are, the Clebsch-Gordon coefficients that we use to SU2 to combine angular momenta and resolve them into different components. Also used for SU3 flavor in my childhood. and for many other things. So these are actual people, and they have a connection with Erlangen. Noether had the education of a young woman from a community with some aspirations. So she went to the local school for young women. In 1900, she took the Bavarian state exam for teachers of French and English. The preparation at her school was really to become tutors of foreign languages for the next generation of young women. She was not able to enroll in the University of Erlangen because women were not, at that time, admitted to the German universities. The Erlangen Academic Senate had made an official pronouncement in 1898 that the admission of women would overthrow the entire academic order. She was permitted to audit. This seems very backward to us today, but I looked into the practices of American universities. I'd be interested to know what they were in Poland, because in American universities, while it's true that a few women took PhDs in the late part of the 19th century, the first at Cornell, the second at the University of Chicago, my university, Yale, did not admit undergraduate women until 1969. Although they had taken graduate students from 1892, and there had been science postdocs early on. First woman PhD was in 1932. Women had been on the faculty since 1920, but not tenured until the 1950s. First tenured in physics in 2001, and then in math not until 2013. Princeton, another place where I've spent time, first admitted undergraduate women at the same time in 1969, the first full-time graduate student in the university in 1961, first physics PhD in 1971, first tenured professor in 1968, in physics 1998. Berkeley and some of the other land grant schools, as they're called, the state universities, admitted women as undergraduates from the earliest times. First physics PhD was in 1926, but the first woman on the physics faculty, again, someone I know, tenured only in 1981. So the US was not more advanced than the German universities, not particularly more advanced in the admission of women. But it was possible to audit classes in German universities with special permission. So while Noether was taking the usual courses for young women, he was also taking private tuition from two mathematics professors, one in Stuttgart, one in Erlangen. And on this basis, she petitioned the rectorate of the universities at Erlangen to be able to audit courses. And it's a very interesting letter because she describes herself as the obedient Noether in the beginning and end of the letter. And eventually she was granted tuition to audit courses. On that basis, she passed the university qualification, did her no good at Erlangen, which still wasn't taking women, but was allowed to go and listen to courses at the University of Göttingen. And in her first semester there, and only semester there, she heard lectures given by Schwarzschild, Minkowski, Klein, and Hilbert. That's quite an introduction to a first-year student, and I think it would either crush you or confirm you in your desire to learn about physics and mathematics. After one semester, the University of Erlangen relented, and she was admitted as a student of mathematics. There she took her PhD under Gordon. She was his only student. And it involved a huge computational problem of computing 331 invariants of a homogeneous polynomial. Gordon himself was regarded as quite an unusual character. It seemed that he would roam the streets of Erlangen, going around smoking a cigar. He would stop at a cafe and have a beer or two or three, and then he would return to his office and write down an entire paper. He is particularly celebrated for one paper in which there are something like 20 consecutive pages of formulas with not a single intervening word of narrative on them in on an obituary form done by Emmy Noether and her father. He's described as a maker of algorithms. So this was his great desire, somebody who wanted to make useful computation. Emmy Noether later described her PhD thesis as Mist, a very colorful German term meaning dung. So she wasn't taken with it. It really didn't allow her to show her inventiveness, but only her computational skills. Sure, again, something to have. It's probable that she was the second woman PhD in mathematics in Europe at the time. And immediately after taking her PhD, she was allowed to serve as an unpaid member of the Erlangen Mathematical Institute. There, in addition to her father's presence, the presence of her teacher, Paul Gordon, there was a new faculty member, Ernest Fischer, who was more interested in what was becoming modern mathematics and was a great intellectual influence on her and opened her up to the idea of creating mathematical forms rather than spending her time making calculations. In 1915, she was invited to Göttingen by Klein and Hilbert. It was really at that time, certainly in Germany, probably in the entire world, the Mount Olympus of mathematics. On the history page of the university, you can find a list of the famous people who were there. And even physicists know a large fraction of the names that you see in the right-hand column there. So it was a stupendous place for a young person to be, and she really blossomed there as a scientist and maker of mathematics. I have not yet visited Göttingen, but in the entrance room of the Mathematical Institute Library, there is a cabinet, a Giftschrank, poison cabinet is the literal translation, but a cabinet of treasures, which has mathematical treasures from the early years, including 40 years of notes taken mostly by Klein. Here's an example of one that you see in the center of the photograph of all these years of seminars. So it makes you wish that, first of all, you had the graphical skills of Felix Klein, and second, that when you were a young person, you had started the protocol of copying down all the important things that you had learned in seminars over the years, instead of just nodding and saying, oh yes, I understand. In 1915, Klein and Hilbert put her forward to take the habilitation by giving a lecture to become a Privatdozent in Göttingen. The Math Science Department of the Philosophical Faculty gave its unanimous support. The unanimous support was a little measured. Here's one example from Edmund Landau. Here is his postcard from one of the bookstores in Göttingen. He wrote, I have had up to now uniformly unsatisfactory experiences with female students, and I hold that the female brain is unsuited to mathematical production. Miss Noether seems to be a rare exception. So that was the supporting letter. I wish I could say I'd never read a letter of that kind, but at least some years ago I did. So that was his referee report. The Historical Philological Department of the faculty opposed, citing their concern that seeing a female organism might be distracting to the students. So the university administration took no action, which meant that the permission was not granted, never turned down. So she did not take her habilitation at that time. She was, however, permitted to lecture under Hilbert's name. The idea was that he would announce a course with the assistance of Fräulein Noether. She would give the lectures. Maybe Hilbert would appear at the first lecture and the last lecture, and she could be the real teacher of record. In 1917, they tried again. She had been invited to visit Frankfurt University. And so they said, oh, you have to let us, you have to permit us to give her the habilitation. Otherwise, Frankfurt will steal her. But the administration now of the Ministry of Education wrote back, not to worry, there's no chance that Frankfurt will have the permission either. Your worries are completely unfounded. She will not be given the right to teach there or at any other university. So there's no concern that you'll lose her as an external lecturer into Frankfurt University. It shows that administrations have their own way of thinking and their own language and writing things. So in 1919, after Germany had lost the war and the Weimar Republic came into being, the legal status of women changed, and her habilitation was granted on the basis of the paper famous to physicists on invariant variational problems. Now, 1918 was another important date in the application of Noether's theorem, even if it wasn't mentioned. This was the time that Hermann Weyl made his first attempt to give a unified symmetry-based theory of all of the fundamental interactions that he knew at that time, electromagnetism and gravitation. He speculated that you could derive such a theorem from making scale transformations, changing the unit of length or the measure of time at every point in space and time independently. This failed for a number of reasons. It made, as Einstein pointed out to him, it would have made a path dependence, which wasn't present in the real world. And of course, we now know that it was the wrong symmetry because quantum mechanics hasn't been invented yet. And the right symmetry to derive electromagnetism is a quantum mechanical phase symmetry that is a local symmetry. After criticism from his friends, Einstein, Fock, and others, by 1929, after the invention of quantum mechanics, Weyl reformulated his ideas and indeed was the first to derive quantum electrodynamics, or at least non-relativistic electrodynamics, quantum electrodynamics from a U1 local symmetry. In 1931, Dirac invented QED, discussed something a bit mysterious at the time called the non-integrable phase. And finally, in 1959, Aharonov and Bohm established that potentials contain too much information, fields too little, but path-dependent phase factors, just what we get from the application of a phase-dependent, position-dependent quantum mechanical phase, contain just the right amount. Interestingly, Weyl, by 1955, so late in his life, said that the strongest argument for my theory seemed to be this: the gauge invariance corresponds to the principle of conservation of electric charge, as the coordinate invariance corresponds to the conservation law of energy and momentum. It was something quite mysterious. Weyl was a great supporter of Noether, we'll see subsequently, but he never seemed to make explicit reference to her theorem, I guess because he had independently come up with his restricted form of her theorem, but he never seemed to give emphasis to the idea that both the conservation law and the idea that you could derive a symmetry were contained in the two theorems that Noether presented in 1918. Now, what about charge conservation? Well, charge conservation is known empirically to be very, very good. If you look in the particle data booklet, the best limit at the moment is a lifetime of more than 10 to the 28th years from the Borexino experiment in the Gran Sasso laboratory, looking for the disappearance of charge, an electron decaying into a neutrino and a monochromatic photon. Where does this come from? Where does the conservation law come from? Well, our first tendency might be to say, what comes from Maxwell's equations? But in fact, Maxwell's equations were built to conserve charge. The addition of the displacement current to Ampere's law is necessary to ensure the conservation of electric charge. You might say that phase invariance, theorem 1, in which we changed the convention for a real quantity everywhere in space and time, and indeed that gives you a conservation law. The shortcoming there is that the conserved quantity could be electric charge, it could be baryon number, it could be any additive quantum number of that kind. And so it's really when you use local phase invariance to derive the full theory of quantum electrodynamics that you see the connection with the full content of Maxwell's equations. So this paper of hers made waves in general relativity circles, but it was not otherwise a sleep instant sensation. Our friends at inspirehep.net, the database of publications, would call it a sleeping beauty. Now, Heisenberg, you will know, was a great partisan of symmetries, great applier of symmetries, an inventor of symmetries. He would later say in discussion with his colleagues, in the beginning was the symmetry. That is certainly more correct than the Democritean thesis. In the beginning was the particle. The elementary particles embody the symmetries. They are the simplest representations, but they are only a consequence of the symmetries. But he confessed to Yvette Schwarzbach that he had probably never read Noether's papers, and it didn't penetrate into quantum theory, and so I didn't realize the importance to that paper. Now, the irony is that the modern application, the first modern application, is to non-abelian gauge theory, specifically a theory based on isospin symmetry, and it was Heisenberg who invented isospin symmetry. Now, we all have had the experience of hearing something and not being able to know what to make of it at the time, and then we, many years later, may figure out why it was important. That is, this is the source of many priority controversies in which we hear something and don't internalize it. So I think the physicists, even though they were getting in large numbers, were preoccupied with inventing and interpreting quantum mechanics. They didn't have internal symmetries at their disposal, so they were just not ready to make full use of Noether's second theorem. What's more mysterious to me is that the idea that energy conservation and time translation invariance are coupled did not dissuade Niels Bohr from entertaining the possibility of energy conservation. So many physics students learn, especially when they learn about neutrino physics, we learn that in the puzzlement over the continuous spectrum of beta rays and beta decay, electron energies and beta decays, Bohr had entertained the possibility that for microscopic processes, things done on the quantum level, maybe energy conservation was a statistical statement and not an event-by-event statement. But it was also the case that even before that, Bohr, together with two other serious people, Kramers and Slater, had entertained the possibility that energy conservation was only statistical in Compton scattering, photon-electron scattering. This was put to rest when the momenta of both final bi-state particles were measured. But not only was Bohr himself not dissuaded by this, nobody seems to have raised the objection, either you can't do this because we trust that the laws of nature are invariant under time translations, or, you know, it would be very serious if this turned out to be the case because it would undermine time translation as a symmetry of the interactions. So,
Please, 10 minutes.
It will be interesting to see 20, 30, thank you, 20, 30 years from now, what we've overlooked that we should have known about. So in Göttingen, Emmy Noether became known as the mother of modern algebra, the study of rings and ideals. She finally became an extraordinary professor. She visited Moscow and Frankfurt, together with her man with whom she was working in parallel in the invention of modern algebra, Emil Artin. She received an important prize. She was the first woman allowed to give the plenary lecture at the International Conference of Mathematics in Zurich. She was an editor of the Mathematical Annals. And she was the person out of this entire roster of great mathematicians in Göttingen who had the largest followers. She had a large number of students, essentially all men, reflecting the time. And they were known for marauding around the streets of Göttingen and talking in loud voices about mathematics. They were known as the Noether Boys. And she was known to her male colleagues as Der Noether, the male article, which I think was not a term of endearment. They tried to excuse it because it showed that she was as strong in mathematics as any man, but it wasn't a very charitable thing to do. Anyway, she had a career that was taking off, and she had many proteges who went on to develop things. Then came the Nazification of Germany, and here is an article from the local newspaper in April of 1933. 6 professors set on vacation or on leave, of which people that we may have heard of, Felix Bernstein, who was the inventor of biostatistics, Max Born, future Nobel laureate Richard Courant, famous mathematician and father of 2 physicists known to me, Hans and Ernest, and Emmy Noether, all were pushed out of their positions. By September, it became really serious. Her permission to teach was revoked, and she had to leave the country. Luckily for Emmy Noether and for many other people, the presidents of American universities moved with uncommon speed to set up the possibility for people who were being driven out of Germany to come to the United States and have at least temporary positions. Emmy Noether was given a position at Bryn Mawr College in Pennsylvania. It's near Philadelphia. Beautiful suburban campus. It was a women's college from its earliest days. But from its earliest days, and among the famous women's colleges, it was known in particular for preparing women for careers in mathematics and science. And so although Emmy Noether was not perhaps ideally suited to teach undergraduates, this was a place where she could find a good refuge. They already had some graduate students, they imported some others and created postdoctoral fellowships for people to work with Emmy Noether. And it's about an hour's drive to Princeton. So a provision was made for her to go to Princeton and visit the Institute for Advanced Study, which was just beginning at that time, and in which she could meet other great mathematicians, including some people that she had known before. And she went there once a week and lectured at the Institute for Advanced Study. She described it as one of the happiest times in her life, even though it was temporary and insecure position. And then in the spring of 1935, she had a surgery that was supposed to be routine to remove a tumor. And after a couple of days of apparent recovery, she died. She died apparently of a cerebral hemorrhage that was unrelated to the surgery, or not directly related to the surgery. But that was a swift and unexpected death for her. Einstein, prodded by Hermann Weyl, wrote an appreciation to the New York Times, in which he talks about her being the most significant creative mathematical genius thus far produced since the higher education of women. So maybe a little measured, but still very, very high praise. She and Einstein had never worked together, but he had noticed her work from an earlier time and prodded by Weyl made this testimonial. Her ashes are buried in the cloisters of Bryn Mawr College. There's a simple marker that you can see there if you visit. And let me just close by giving a couple of quotations. One from Hermann Weyl, who gave a very long and detailed eulogy at her memorial service. He says, "I have a vivid recollection of her when I was in Göttingen as visiting professor in the winter semester of 1926-27 and lectured on representations of continuous groups. She was in the audience, for just at that time, the hypercomplex number systems and the representations had caught her interest. And I remember many discussions when I walked home after the lectures with her and von Neumann, who was in Göttingen as a Rockefeller Fellow. fellow, through the cold, dirty, rain-wet streets of Göttingen, I have this image of Emmy Noether, who lived for mathematics, being oblivious to the terrible weather and stopping these guys who just wanted to get out of the rain on street corners to discuss a point from the lecture. She was really a force of nature. He says, when I was called permanently to Göttingen in 1930, I earnestly tried to obtain from the ministerium a better position for her because I was ashamed to occupy such a preferred position beside her, whom I knew to be my superior as a mathematician in many respects. So even though people speak well of the dead at memorial services and in eulogies, this is a very powerful testimonial to his appreciation for her as mathematician. And one more from Bartel van der Waerden. Van der Waerden wrote a couple of books on modern algebra that were known to me and my contemporaries. He described them as transcribing or translating for ordinary mortals the lectures of Emmy Noether and Larkin. And he describes her style in this way. This entirely non-visual and non-calculative mind of hers was probably one of the main reasons why her lectures were difficult to follow. She was without didactic talent, and the touching efforts she made to clarify her statements, even before she had finished pronouncing them, by rapidly adding explanations, tended to produce the opposite effect. And yet, how profound the impact of her lecturing was. Her small, loyal audience, usually consisting of a few advanced students and often an equal number of professors and guests, had to strain enormously in order to follow her. But those who succeeded gained far more than they would have for the most polished lecture. She almost never presented completed theories. Usually they were in the process of being developed. Each of her lectures was a program, and no one was happier than she herself when this program was carried out by her students. Entirely free of egotism and vanity, she never asked anything for herself, but first of all, fostered the work of her students. She always wrote the introductions to our papers. So I think I'll stop at that point. In the remainder of the slides, you'll see some more quotations from people who were her followers and references to other places where you can learn more about the work, and in particular the mathematical work of Emmy Noether. And at that point, I'd be very happy to take your questions and comments. Thank you.
Thank you, Chris, for this beautiful talk and interesting subject. Now we have time for questions. So if you would like to ask a question, please raise the hand.
I have one comment, if I may.
Okay, Professor Jacek Wosiek from Kraków.
Yes, I remember reading somewhere that Emmy Noether didn't particularly care about way she was dressed. And at one lecture, she had a trouble with her petticoat. And then after unsuccessful attempts to solve it, she finally got nervous, and she approached the nearest dustbin. She tore it off and threw it away. And then, visibly relieved, she continued with her lecture. Thank you.
That is a kind of focus that we could all wish for, I guess. Thank you.
Other questions or comments or remarks? So it was a difficult time for her when she lived. Not like now. Now it's much easier for women to make a career, although not so. Still, there are some problems.
Still, there are problems. That's right.
Yeah.
She was, well, she was held back by being a female, obviously, from the beginning. She was triply cursed when the Nazis started their purges because she was Jewish, she was a pacifist, and she had connections with Russian mathematicians and visited Russia. So the government.
And she was a woman as well.
Although it's not obvious. But yeah,
and she was a woman.
But as you see, others who were not women were also driven out. I think her, the fact that in the United States, even though it was remarkable that she found a happy place in the United States, had she be a man, she herself might have had a position at the Institute for Advanced Study. There are now some letters that the Institute is making available that suggest that in 1935, they were considering making a permanent home for her. It never came to pass. And Princeton University itself was quite hostile to women at the time. Or the real separation of the Institute and Princeton had to take place for that to be really considered.
Yeah. Other questions or comments?
What was the case in Poland? When was it common for women to enter universities?
Well, that's a good question. Maybe Professor Wróblewski would know well. Andrzej, do you know this?
Okay, I can add a few comments. In Poland, women were admitted to universities at the beginning of last century. And before the Second World War, there were already quite many PhDs granted to women. And there was one woman professor in physics, or rather physical chemistry, Dora Bialska, who achieved the nomination for professorship of a chair at Lwów Polytechnic. So this was all during the time when in the United States, women still had a lot of trouble to get tenure. In Poland, it was possible. However, the number of students in mathematics, physics, and exact sciences was not very large. After the Second World War, the situation changed completely, and we now have quite a number of women professors in exact sciences in our universities.
Yes. Thank you.
Thank you.
Any other questions or comments from?
Hello.
Yes.
Can I ask a question? Whether she has any physical, any actual interaction with the physicists based on her research or theory?
I'm sorry, can you say that again, please?
Do you have, I mean, did she have any interest in theoretical physics with the interaction with well-known physicists?
Not so far as I know. So as the, there was this interaction with Klein and Lee, and Klein and Hilbert, which had to do with general relativity. And Einstein had read their correspondence. I think he was being kept abreast of these things. But I don't know of her taking any interest in applying what she did in theoretical physics. And once she arrived in Göttingen and had switched to modern algebra, they were just making innovations in series. And it is a very interesting question. I alluded to a little bit before that there was this great collection of mathematicians in Göttingen, great collection of physicists, and they seem not to have as much connection. I mean, we now can look back and say, why, they were doing the same thing or almost the same thing. Why didn't they notice each other? And I think it must just be that they were both so, both groups were so focused on what they did. Now, there is the famous 2-volume set of books by Courant and Hilbert called Methods of Mathematical Physics, I think, that people of my generation relied on. And that is one of the few places where there is any reference at all in the literature that I studied in the early times to Noether's theorem. There's a passage of about 2 or 3 paragraphs from Courant and Hilbert calling attention to the application to the Euler-Lagrange equations for mechanics. But I don't know of any applications that she attempted to make.
So at that, actually, when she was in United States, she's in the Princeton, so she might interact with the Albert Einstein or other well-known physicists in that institute. So I wonder, it's interesting. I don't see any interaction or Einstein himself never used Noether theorem, right? Directly.
I think that's correct. I think you bring up what would be an interesting study for a historian or physicist with an interest in history based at the Institute for Advanced Study. And that is to look into what precisely were her interactions with the people there. Part of it, what's recorded in the places that I read are the joy she had in interacting with Weil and other people that she had known in Europe. But I don't see any references to direct interactions with Einstein. As I say, he was aware of her quality. But we all, I think back of my own career, and I've been in the presence of fantastic people, but I was busy doing something else at the time, so I didn't take full advantage of them. I think we're all guilty of this.
Thank you very much.
Other questions or comments? Michał Karpiński, yes.
Thank you for a very interesting talk. In your talk, which is about the century of Noether's theorem, you focused mostly on the first half of this century. I was wondering if you could tell something about more recent developments of the second half of the century, or maybe the last 20%. What would be the most important consequence of Noether's theorem discovered, for example, in the...
Well, thank you very much for that, because I realized that I panicked and stopped one slide before I meant to. So let me say that the rediscovery of Noether's theorem by physicists came with the work of C.N. Yang and Robert Mills in 1954. So they tried to make a theory of the strong interactions among protons and neutrons that was based on isospin symmetry. Now, isospin we know is based on the notion that proton and neutron have almost the same mass. We say if you neglected electromagnetism, they would have the same mass. And we usually use that as a classification symmetry, as a symmetry for relating strength of interactions and so on. So their idea was, following Noether's second theorem, to impose this freedom of choice of who is a proton and who is a neutron independently at every point in space and time. And they made such a theory, as we now know from Noether's theorem. Of course, the construction we go through, it takes a couple of pages of arithmetic to do it, not very much. And you find that there are things like charged photons, massless charged particles, that mediate the strong interaction between protons and neutrons. Perfectly respectable theory that doesn't correspond to our world. And so, it's one of these brilliant ideas that happen to be applied to the wrong situation. When I was a young person at Stony Brook in Yang's Institute, he had just learned that gauge fields are analogous to fiber bundles in mathematics. And we had one of the great heroes of fiber bundles, Jim Simons, in the same building with us in the mathematics department. So Yang arranged a series of encounters between the physicists, theoretical physicists, and the mathematicians. And I remember at the first one of these, Yang explained to the mathematicians his motivation for constructing gauge theories, which was this idea that you must have the freedom to choose independently at each point in time this convention. Well, most of the mathematicians had barely heard of what a proton and neutron was. And the notion that you could make some decision about conventions, they regarded, I think at first they thought that he was sort of joking with them. This couldn't really be the basis for this deep theorem. And then the next week when Jim Simons told us how he had come on the concept of fiber bundles, we physicists were equally puzzled. So it's an application of Noether's theorem, and Yang, to this day, he's still alive, about to have his 100th birthday, has been one of the people who really attributes deep significance to Noether's two theorems. So it wasn't the right theory of the nuclear forces, which after all are mostly mediated by pion exchange. There are some vector meson exchanges that enter, but those are not for massless particles. However, in the early 1970s, applying this very idea to SU3 color symmetry leads us to the highly successful and indeed magnificent theory of strong interactions among quarks and gluons, quantum chromodynamics. So the idea has learned to live another day. And now when we make speculative unified theories of all the interactions, the tool that we rely on first is the idea embodied in Noether's second theorem, that we can make independent choices at every point in space and time. So thank you for reminding me that this was the culmination of my talk, and I should have gotten to it in the beginning.
Okay, so
thank you.
Are there any urgent questions or comments? So if not, I think it's time to thank our speaker, Chris. It was a fantastic talk. Thanks a lot.
Thank you very much.
Okay.
And next time in Warsaw.
Thank you very much. So we close our meeting.
Thank you.
Thank you. Bye.
Bye-bye.